This is problem 1 from chapter 17. In this problem, we want to determine the moment of inertia IY. So the subscript y tells us that y is the axis of rotation. So we're looking for the moment of inertia about the y-axis. For the slender rod, the rod's density and cross-sectional area are constant. We are going to express the result in terms of the rod's total mass. So we want to find the moment of inertia about the y-axis. And we have our diagram here. And if we go to our equation sheet, we want to use either equation 17.1 or equation 17.2. This is for equation 17.1 and this is for equation 17.2. Almost always we're going to use equation 17.2. The only case in which you can actually integrate with respect to m is if r is the same for all the little elements of mass that you have. Okay, so let me copy down my equation here. Okay, and remember that we compared what we have here to what we did in Physics 261 when we looked for the electric field. And back in Physics 261, we were given in the Spiral Physics book 8 steps to successfully find the electric field for a continuous charge distribution. So we don't have 8 steps in this case because the equation's not exactly the same, but we're going to use some of those same steps in this problem to help us successfully do this integral. So the first step is to carefully identify and label the location of the differential element. Now I'm only doing this now because it's the first time we have a problem like this, so you don't always have to do this, but I think it's going to be helpful now. So identify and label the location of the differential element. So in equation 17.1, this differential element was dm. So this little element has a mass dm. It also has a volume dv. Okay, and if I was using equation 17.1, which would be equivalent to what we did in Physics 261 when we had a dq, I would have to then take my dm and write an expression for that using the fact that the mass density is equal to dm over dv, and then I get dm is equal to rho times dv. So that's how we get equation 17.2. Okay, now I look at the terms that I have in my equation here. So I have r squared. I need to figure out what r squared is. So r is the distance from the axis of rotation, the perpendicular distance from the axis of rotation to the little element that you have here. So that's this distance here. Rather than calling it r, because that distance is along the x-axis, let's just call that x. So now I have r squared becomes x squared. And they told me that the rod's density is constant. So if the density is constant, that can come outside of the integral. So that's going to come out here. Then I have this dv. Well, in rectangular coordinates, dv is equal to dx, dy, dz. That is a triple integral, and you're integrating over everywhere where there is mass. And if you do that for dx, dy, dz, you would get the total volume of the rod. Well, we can't do that here because we also have the r squared or the x squared in our integral, but I can say this: if I were just to integrate dy and dz, that would give me the area because I'm integrating over everywhere where there is mass, and this cross-sectional area here is A, so that gives me that area there. So I can replace, I pulled the row out there, I can replace the dv with dx, dy, dz, and then I have a triple integral. But before I worry about what the limits of integration are, integrating dy, dz over everywhere where there is mass is just going to give me this area here. So that is rho times A. Then we're just left with integrating x squared with respect to x. Okay, and in the future, if you want to skip this step and just go from here to here, That's fine. Now we have to carefully choose the limits of integration. So I'm integrating over everywhere where there is mass. So I start at this end of the rod when x is equal to 0, and I go to this end of the rod where x is equal to L. And now I can do that integration. Integrating x squared with respect to x gives me x cubed over 3. I have the rho and the a out in front. My limits of integration are from 0 to L. So this gives me 1/3 rho times a times L cubed minus when I put in the lower limit of integration, that's 0. Okay, but I do not want to leave the answer this way because they specifically told me in the last sentence of the problem to express the result in terms of the rod's total mass. Well, this is the mass density of the rod, and we set up here that's equal to the mass of a small differential element over the volume of the small differential element, but that is also equal to the total mass over the total volume. So I want to use that to rewrite my expression here to be in terms of the mass rather than in terms of the volume. Rather than in terms of the density. Okay, the volume of this rod, if this area is A and this distance is L, the volume is A times L. So for my density, I have the mass over the volume A times L. Then I can take this and put it in there. So now I have 1/3 times the mass divided by the volume, which is A times L, times A times L cubed. So A and A cancel out. This L cancels out with 1 power there and leaves you with a 2. So finally, I have 1/3 times the mass times L squared. Okay, and this is the moment of inertia about the y-axis. And that concludes problem number 1.